Okay, we want to now talk about two things, curvature and the binormal vector. First, curvature. We'll do the binormal vector in another video. Intuitively, if I'm driving a car around a curve and I'm going like this and now like this and now like this, well, then if I'm looking straight ahead, my unit tangent vector moves like this, doesn't it? Okay? Now, if I go around the same curve a little more slowly, it's more like this. Okay? So if my unit tangent, well, the curvature of my curve is independent of how fast I drive around it. If I'm driving around a circle, and anytime I'm going around a smooth curve, I'm temporarily on a circle. Now if the curvature of the circle changes, I'm temporarily on a bigger or smaller circle. And maybe the circle keeps getting bigger, which means it gets easier and easier to go around that curve, or maybe it increases, which means I've got to slow down maybe a little bit. Okay. To get the curvature, if my position vector is parameterized in terms of time, then I have to correct for how fast I go around. I want to say that the rate at which my unit tangent vector changes is somehow related to the curvature, because obviously as I go around a curve, unit tangent vector is changing. Okay? If I'm going around the curve fast, it changes faster than it would if it was slow. So it makes sense to think about how quickly the unit tangent vector changes with respect to how fast I'm moving. So that we would say maybe curvature is the rate of change of direction with respect to distance traveled along the curve. Okay? Now, rate of change of direction with respect to distance traveled. I'm not going to completely make the connection, but if we take the rate of change of the unit tangent vector and divide by how fast we're moving, this is how quickly the direction changes, this is how fast you're moving, then we get the rate of change of direction with respect to the distance traveled. Okay, so this is one of our ways of calculating the curvature, which might be read as a K or a kappa, depending on who writes it and how it's written. Okay, there's not much difference between the lowercase k and the Greek kappa. Another thing we can say about this, and you want to store this away and understand it, this is the magnitude of the derivative of your unit tangent vector with respect to t. This is a magnitude of derivative of your position vector with respect to t. If we did a d big T, d little t, divided by a dr, d little t, it's kind of like a d big T divided by d little t, multiplied by a d little t over a dr. So it's like a d big T over a dr. Okay, which is a rate of change again of direction with respect to distance traveled. Another formula for that I wrote down incorrectly, and you learned this in about the middle of the second semester of a typical calculus course, maybe a little bit earlier. And of course you can learn this first semester too, and actually you probably did. It turns out to be equivalent to this expression that you know from first year calculus. So, this is how we're going to calculate it when we have a curve that's parameterized. This is how we'd calculate it if y was given as a function of t. For example, we eliminate the parameter and express y as a function of x. I think I said t. Y is a function of x.